Hello everyone, my name is Ian Lumsdem. I am a late stage, kind of final few months probably, actually, PhD student, also in the Global Computing Lab at the University of Tennessee, like Jay. And today I'm going to be transitioning us a little away from what Flux is itself, and more how it's enabling and helping applications, specifically for the topic of I/O. So in some previous work, we took this plasma physics application called IPIC3D, and we optimized it for El Capitan to achieve a kind of first of its kind result for planetary scale plasma physics. So plasma physics on the order of a planet like Mercury. But in looking at the data after that work, we found a bit of a bottleneck, that this application spends about a third of its time in I/O, and exacerbating that issue, the I/O is split across 3 different phases. And this is exceedingly common in exascale applications, where they're increasingly bottlenecked by multi-phase I/O workloads. So to solve that, we looked at a unique piece of hardware on El Capitan and Tuolumne called the Rabbit nodes. If you're not familiar, Rabbit nodes differ quite a bit from the conventional storage hierarchy on a system like Sierra. On Sierra, we have burst buffers physically on the compute nodes, and then we've got some system-wide storage. It's GPFS on Sierra, but it could be something like Lustre, as is the case on Frontier. For El Capitan and Tuolumne, on the other hand, we have these near compute node I/O accelerators called Rabbits. And one of their cool features is that you can kind of dynamically provision storage on them just by adding some flags to your Flux script. So some examples of the storage you can provide are ephemeral, kind of temporary Lustre, persistent Lustre, and also XFS, which mimics the local storage you'd have on a system like Sierra. And this is all enabled through Flux. So on the left, you can actually see an example of the hardware of the Rabbits. So the actual accelerator is close to compute nodes. It's connected with both PCIe and the broader Slingshot network through the NICs. And then it's got SSDs, an EPIC CPU, all that. The more interesting thing comes up with the software. El Capitan can be thought of as being divided into kind of 2 spaces. There's the compute node space, which is a conventional HPC system, batch scheduled with Flux. And then there's the Rabbit space, which is actually more cloudy. It's actually managed by Kubernetes with a collection of containers, the topmost one being near node Flash. And Flux serves as kind of the bridge between these 2 kind of separate universes, if you want to think of it like that. So when you run a job, Flux talks with near node Flash to provision the storage. It also spawns a service called NNF client mount to actually let your job know where that storage is. And then from then on, NNF client mount provides mount points to the actual storage on the Rabbit nodes. I also want to emphasize that when you're using Rabbits, Flux will edit its job lifecycle some, and in particular, Flux makes use of its graph-based scheduling component called Fluxion to actually schedule the storage on the Rabbits. So the resource graph, the resource representation of Flux, looks something like what's in the red box on screen here, and it uses essentially a very complex graph matching approach to actually identify both what compute resources you need and what Rabbit storage resources you need. Moving back a little bit to the research side, in the research work associated with this, we applied a 3-step methodology to IPIC3D to optimize its I/O and resolve that 33% 3-phase bottleneck that we talked about at the top of the poster. In step 1, we analyzed IPIC3D's I/O while writing everything out to Lustre to identify dominant phases and quantify their performance. So each column on the table here represents the characterization of a different phase of I/O. In step 2, we converted each phase, essentially each column in the table, into a configuration of the IOR benchmark and ran it against various storage solutions on the Tuolumne system, the kind of smaller, more open version of El Capitan. And then in step 3, we integrated these results back into the application and compared against our original write everything to Lustre version. In doing this study, we found 3 key insights applicable beyond IPIC, namely hybrid I/O strategies with multiple file systems in a single application can deliver superior performance. I/O workload characterization is critical to actually do the mapping of access patterns to storage backends. And chassis level or rack level storage accelerators like the Rabbits enable dynamic adaptability for diverse I/O workloads. And applied to IPIC specifically, these insights led to up to a 4.85 times improvement in I/O throughput, a reduction in the share of runtime from 38% to 11% for I/O, and an overall application speedup of 1.45 times. If you're curious about this work, the 2 QR codes on the bottom point you to the paper about our work with IPIC3D and optimizing for LCAP, and our paper in the RexIO workshop at Cluster last year about the actual Rabbit optimization of this software. So thank you.